All right, thanks very much for giving me the chance to speak again. So everything I say is going to be joint with Ben Baker. And what I want to do is I want to basically talk about how to bring in this new ingredient of ominimality, which has been useful in the world of Shimura varieties, to the context of hard structures, variations of hard structures. And somehow variations of hard structures are much more ubiquitous than Shimura varieties, but somehow they lack the same algebraic structure, and we're hoping to sort of remedy that with what I'm going to talk about today. So let me start by just giving some definitions. So a polarized variation of, a polarized hard structure of some integer weight n consists of the following objects. So first, we're going to have a lattice. So a free abelian group of some positive rank n, m. We're going to have a bilinear integer valued form q on this lattice, which is either symmetric or anti-symmetric, depending on whether n is even or odd. And finally, we're going to have a decomposition of the complexification of our lattice, L tensor C, into pieces H, P, Q, which are complex vector spaces, satisfying the following two properties. So first of all, if you complex conjugate H, P, Q with respect to the complex conjugation given by this tensor product, you get H, Q, P. And second of all, if you look at I to the P minus Q times Q of V bar, this is positive. On HPQ, except it's obviously 0 on 0. OK, so these three things define a polarized hard structure. The sort of the polarization is what's referred to by Q here. And the prototypical example that sort of motivates this definition is the following. We take X to be a smooth, projective, complex variety. And then we let L just be the usual Betti cohomology of our variety X, modulo torsion. So we don't want any torsion pieces, we want a free abelian group. We have, if we tensor with the complex numbers, we just get the usual cohomology with complex coefficients. And then we have a Dolbeau decomposition given by with respect to sort of P holomorphic, Q anti-holomorphic forms. And what is Q? So Q is essentially given by cup product. Since X is a projective variety, we have sort of an integral Kähler form on X, given by its projective line bundle, its ample line bundle. And we just define Q of gamma 1, gamma 2 to be the cup product of gamma 1 with gamma 2 together with this class on X to the power of the dimension of X minus n. So this will be an element of H twice the dimension of X, which isomorphic to 0. So this is sort of the definition that motivates. Oh, no. Yes, you're right. I have to restrict to, in order to get this, you mean?
Yes, to positivity.
To get the positivity, yeah, that's right. You're right. I didn't prepare this adequately. So I can just add the word prim somewhere and probably be fine. Yes, let me do that. Let me add primitive part here. And now I'm good. Thank you. All right. So yeah, this is the canonical sort of example that motivates a definition of a hard structure. But so even though this direct sum decomposition is nice to work with, it ends up being more natural to record things in the form of filtration. So let's define the filtered piece Fp to just be the direct sum over P prime at least P of H P prime Q prime. And so then we have a descending filtration starting from F naught and going down. And from here, we can recover the HPQs just as in the following way. If we look at Fp and intersect with F Q plus 1 bar, that's what I have here, when we get HPQ. Or is it FQ bar? Yeah, Q bar. Sorry, with my notation, that's right. You get FPQ. So the reason that it's sort of more natural to record things in terms of the filtration is because we want to study variations of hard structures, sort of families of hard structures over a base. And given how this is our canonical example motivating definition, it's natural to start from sort of looking at variations, just smooth projective families, and seeing what properties the resulting hard structures, variation of hard structures gives us. And in particular, if we use decomposition, we can't expect these things to vary holomorphically because of the complex conjugate here. So even for elliptic curves, the H10 piece moves holomorphically, and the H01 piece moves anti-holomorphically. Whereas if we record things in terms of filtration, then this whole thing varies holomorphically in families. All right, so one more definition. We say that a vector v in L, actual integral vector, is Hodge if v, this can only occur in even dimension, is of pure weight. And since v is its own complex conjugate, it has to be in weight n over 2. So this is important, of course, because of the famous Hodge conjecture, which tells us that if we have Hodge vectors in this context, they correspond to actual subvarieties representing that vector. All right. So now that we sort of have things laid out in this way, we want to talk about varying these guys in families. And so let me define omega hat to be just triples of LQ F dot, where now I want these to be given with a basis. So I want to record an actual isomorphism from L to Z to the M. And what I mean is I'm going to record L, record the pairing, and I'm going to record the filtration, and not really pay attention to this positivity condition over here. So this is some sort of symplectic, I'll call it a symplectic Grossmanian. It's basically just a Grossmanian, but we also have to insist on some properties with Q that the filtration satisfies. So it's a nice projective sort of manifold. And inside here, I'm going to call omega sort of hard structures with a basis. So in other words, I'm going to look at the open subset of these guys. And there is an open subset where when you intersect like this and get these HPQs, you in fact get something which satisfies these conditions. So this is sort of familiar.
You could have said you are not in the case PQ and X.
Oh, yes, that's right. I should have mentioned that here as well. Thank you. That's right. So we also want, that's right. You want these guys to be 0 if p plus p prime is not equal to n. Thanks. Yeah, sorry. That's an important condition. So the HPQs are isotropic with respect to q. OK, cool. So this is sort of familiar to the setting of Shimura varieties, where we sort of have some symmetric space, and there's an open subset with its compact dual, which is some actual projective variety. For example, this could be the upper half plane, in which case this is just the projective line. OK, so then we can look at G. Let it be the automorphism group, the algebraic group, which is the automorphism group of L, which respects this pairing Q. And then we have an action of GC on omega hat, just by acting on this filtration. And GR preserves omega. This action is actually transitive, so it can't preserve omega, but the real points do. Again, much like the upper half plane. And if we want to talk about the moduli space of hard structures, we just look at omega mod GC, and after some coarseness issues, this is the moduli space of polarized hard structures, where of course I've fixed a certain type. I fixed the dimension of these guys, and I've also fixed the isomorphism type of LQ, the lattice with the pairing Q on it. OK, so one big issue with this space is that this is not, in general, an algebraic variety, even though it is a complex manifold or a complex orbifold or something. So let me also mention, I'll say this in words, I won't sort of write it down. Shimura varieties can sort of all be placed in this context as long as we allow slightly greater generality. So Shimura varieties aren't actually moduli spaces of hard structures, but they're what are called sort of Mumford-Tate domains. So by insisting that certain vectors, or in general, you got to look at tensor products and look at things there, that certain tensors are Hodge, integral tensors are Hodge, we get Mumford-Tate domains. And they're, in some sense, the correct level of generality to work. Here, though, I don't want to say too much about that. All right, so now if we want to talk about variations of hard structures, so I'll write as VHS. So what are they concretely? Well, concretely, we have some complex base S, and we have a local system, L over S. So L is an integral local system. And now pointwise, we want to give it the structure of a polarized hard structure of some weight. And so what we do is we can look at L tensor O. So L with coefficients and holomorphic functions over S. And we just give some filtration inside here. So in other words, we're pointwise. If you restrict this to every point, you get a filtration of that sort over there. And we insist it varies holomorphically, is the way to think about this. Satisfying something called Griffith's transversality. And what that says is Okay. So in other words, if I differentiate, I don't want to say it precisely, but if I differentiate how the pth piece moves in any direction, this has to lie inside the previous piece of the filtration at p minus 1. So you can prove that this actually is satisfied inside, inside smooth projective families. And so we sort of insist this is true for variations of hard structures abstractly. So one important note is that in Shimura varieties, this condition ends up being empty. It's automatically satisfied. That's easy to see for weight 1 hard structures because it's sort of just empty by definition. Yeah. Okay. So in other words, variation of hard structures are maps from S to omega mod gz, which satisfy Griffith transversality. Which in this language you could record as just the derivative of this map lands inside a subbundle of the tangent bundle, which is sort of canonically given. All right, and I'm being a bit coarse here because there's some monodromy issues and such. Not every such map gives you a period map and stuff like that, but not every such map gives an extra variation of hard structures, but this is sort of close enough. All right, so that's the definition. So now let me switch gears a little bit and talk about the kind of structure we want to put on here in order to get some sort of tameness properties for these sort of period maps. So let's call these sort of maps. So phi is a period map. OK. All right, so the idea behind what we're going to do is we're going to say that, OK, these maps aren't algebraic. Even so, we can sort of describe these maps using not all holomorphic functions, but a very tame subset, which behaves in a particularly nice sort of fashion. And this is captured very nicely by the principle of ominimality. So an ominimal structure. Sorry, say that again?
You know that omega over gz, that gz is big enough to make omega over gz small.
Yes, you do know that. So you know that this group actually acts transitively on omega.
And then you just 3 points are big enough.
Yeah, so just because for semi-simple groups they're big enough, it's semi-simple. Yeah. It's good. Yes, that's right. So I didn't mention this yet, but this acts transitively and allows you to identify omega with gr mod v, where v is compact, but that's right, not maximal compact. Yeah, you can also identify omega hat with gc modulo some parabolic group over here. OK. So let me give a quick definition of what an ominimal structure is. There's I think there's two ways to sort of talk about this. One is to think about sort of quantifiers and admissible functions and things you can build in that way. Or you can talk about it in terms of sets, sort of nice enough sets, which I sort of prefer. So I'll just say it's a collection, so-called S, of subsets Sn, where each Sn is a subset of the power set of R to the n. So concretely, for each n, we're looking at subsets of R to the n, and we're saying which ones of them we're sort of allowing.
What did you define? Ominimal
just just what an ominimal structure is right now. I'll talk about how it gets to a complex variety in a minute. Satisfying the following things. So first of all, for all n, Sn is a Boolean algebra. In other words, if you have two definable sets, you can intersect them and you can take complements, and you can union them. I guess that follows. And you're allowed to take products. That's a definable.
Where is Sn?
Yeah, so Sn is a subset of the power set of R to the n. Yeah, so it's just a collection of subsets of R to the n. So if I take a subset in Sm and a subset in R to the n. Sorry, this is Sm plus n. Yes, I just saw that. Thank you. Right, so if I take something in Sm and something in Sn, and I multiply them, they're in R to the n plus n, and that should be definable. Also, it should be closed under projection. So if we take any coordinate projection from R to the n plus 1 to R to the n, you project Sn plus 1, you get Sn. So this is where the quantifier stuff comes in. This is the.
Presumably the reals, you could do it as a p-adic theory, probably.
The p-adic theory is harder. You could replace the reals with a.
Quantify elimination is
No,
not.
no, no. So of course there's so you could replace the real field with any complete, totally ordered field. That's fine. But ominimality is not the right notion in the p-adics.
Okay.
In the p-adics, it's harder. And as far as I can tell, it's still somewhat being developed. There's it's more complicated in that setting. Because of something I'll write down in a second.
Only quantify elimination is not.
For algebraic sets.
Well, and projection, yeah. The fact, the key, the hard thing is this projection thing. If you're taking
Right.
real analytic, I mean, what do you get to keep track of what you get?
Sure, sure. Let me say a few more things, and I'll address the p-adic question. So this thing, you want to talk about equality. So you want the set which is just x1 equals x2 to be inside S2. So you're going to be allowed to talk about the diagonal. OK, so this is just what a structure is so far, not an ominimal structure. The ominimality, and by the way, ominimal stands for order minimal. The ominimality comes in this final condition that if you look at S1, so all the one-dimensional definable sets, so S1 consists of finite unions of points and intervals. So basically everything you can write down using the less than relation without using quantifiers. So it looks like this is sort of a weird condition at first.
Interval things, open interval.
Either one is fine. Yeah, so open intervals and points, but if you include, but you can, yeah, but you're allowed infinite intervals. That's right. So yeah, at first it seems like, well, all the interesting sets are in higher dimension, and you're only requiring something about one-dimensional sets. That's kind of weird. But of course, you're allowed this projection and intersection stuff. So it's really saying that high-dimensional sets can't get so complicated. Otherwise, they could define some weird one-dimensional sets. And sort of maybe somewhat counterintuitively for someone like me who comes from arithmetic is that Z is sort of the worst set around. If you can get Z, then all hope is lost. So you only want to get finite unions of points in one dimension. So yeah, Peter, this is sort of the condition that becomes harder to define an analog of in the p-adics, right?
It's just that Paul Cohen gave a proof to quantify elimination of the p-adics. It's not so well known.
For algebraic, for semi-algebraic sets, you mean? Yes, yes, that's true.
And he gave a new proof of Tarski's theorem as well.
So ominimality should be seen as sort of a weaker property than quantifier elimination in general, is how. Yeah.
But one does not assume that Sn is GLN invariant.
No, but in all the structures I'm considering, that'll follow immediately. Yeah, but in general, one doesn't assume that.
But semi-algebraic is not the correct replacement for 5 in the Peati case?
That S1 is semi-algebraic? No, I think it's not, actually. I don't know, so I'm talking a little bit out of... But I think you have to be a little bit clever with talking about nth powers of things. I think you have to allow... I'm not sure. Yeah, let me just leave it there. I'm not sure. OK, so examples. So first of all, there's the structure RSA, which is a structure consisting of semi-algebraic sets. In other words, everything you can define using addition and multiplication. So it's a smaller structure containing the graph of addition and the graph of multiplication. You throw that in, and then you sort of use axioms 2 and 3 and 1 to generate everything you can, and that's RSA. So yeah, in particular, note real algebraic varieties aren't a structure because they aren't closed under projection. But if you add the less than relation, then you're fine. So this is Ominimal, and this is a theorem of Wilke. Sorry, this is Tarski-Seidenberg. This is the famous Tarski-Seidenberg theorem that says it's quantifier elimination. That's right. So they prove omnimality by saying that you don't need quantifiers. You can define everything in n dimensions just using n dimensions. So then there's the structure Rexp, which is look at RSA and add the graph of real exponentiation, and then do whatever you can over there. And that's proved by Wilke based on the work of Khovansky. The structure is still ominimal. And then there's the structure which always seems to be what's worked with in the number theoretic context I've encountered, which is Rnexp, which is you look at Rexp plus subanalytic functions. Which are functions, analytic functions on a ball, which actually can be defined on a slightly bigger ball, the converge on a slightly bigger ball. And this is Wilke and van der Dries. This is minimal.
Sorry. So you add the graphs of these subanalytic functions on the ball they're defined intersect R.
That's right. That's exactly right. No, what do you mean intersect R? Analytic in R. So let me be concrete about this. So if you take a function f from some m-dimensional ball to R, which converges on a bigger ball, so real analytic and converges on a bigger ball, then you throw in x f of x, where x is in your ball. So this is inside the structure Rnexp. That's right. Cool. Yeah. So I'm not going to say anything about the proofs of these. Well, I can say a little bit, I guess. So yeah. So here, and actually for Rn, which is just Rnx minus the x part, you can do complete quantifier elimination. And so you can show that projection is ultimately unnecessary, from which this ends up being kind of easy. Rexp follows from, well, a lot of things. But this one's, you don't get quantifier elimination here, but you get a certain restricted form of it that's sufficient to prove this theorem. I want to add that sort of, so why do we sort of care about omnimality? Well, it sort of lets you have a lot of things that you would get. I think of it as you get sort of, if your functions were algebraic, you get a lot of properties for free, and you can recover a lot of them in this context. For example, everything definable in an ominimal structure has finitely many components. That's a theorem you can prove pretty easily, and you can prove certain uniformity theorems pretty easily. And I want to mention something which I think is extremely important, which we're going to be using heavily. And it's a theorem of Petersil and Starchenko. And so they pioneered sort of the study of complex analytic geometry in an ominimal setting. And they have the following theorem, which I think of as definable Chow. And it says the following. So let V be a quasi-projective, or it doesn't really matter, algebraic variety. Okay. And take W inside V to be closed, complex analytic. So at every point, it's given by the zeros of a complex analytic function. I'm sorry?
Ordinary complex topology.
Ordinary complex topology, yeah. And you want W to be definable in an ominimal structure, which I haven't said what that means yet. Then W is algebraic. So it's a really powerful theorem, because usually for Chow, what Chow tells you is that if V is a projective algebraic variety to get something complex analytic inside it and closed, it has to be algebraic. And Petersil and Starchenko say, well, forget about that. Just work in an algebraic context. Take any holomorphic closed thing. As long as it's definable in some ominimal structure, it has to be algebraic. So in many different settings, this is sort of ends up being a very good substitute for a missing algebraic structure. So what is it? Yes?
So the quasi-projective variety has already an ominimal structure on it. Does these two ominimal structures, are they compatible or not?
Right. So I was going to say, that's a good question. So I didn't say what definable in an ominimal structure is. So far I just talked about definability as allowing certain subsets of R to the n to be definable. So first of all, if you talk about real manifolds, you can talk about definable manifolds pretty easily just by looking at finite open coverings and maps to R to the n and definable transition mapping, so all that's fine. We're talking about complex varieties, but again, that's OK because C is just R squared, and so you can talk about things in that way. And yeah, so to answer Gao's question, V is quasi-projective algebraic variety, which means it has an algebraic structure on it, and that also gives you every single one of these structures. You just take some affine covering of V. On each one, you put this sort of structure. The transitionary maps are algebraic. They're certainly in all three of these. And so you get a definable structure on V, which is how you can make sense of this.
Okay, so complex semi-algebraic is the same as complex algebraic. So you treat it as real? Or
One more time?
when you say it comes with these structures, you treat it as a real manifold?
Yeah, that's right. You think of V as a real manifold of twice the same dimension, and then it comes with these structures. Mm-hmm.
Will it be true that all minimal things are triangulable?
Are triangulable. So there is a cell decomposition theorem for all minimal things. That's right, for all minimal structures. Yeah.
And does one have finite volume theorem?
In certain contexts, but I'm not too sure about that. Yeah, I mean, in the Shimura context, you do. But in general, I'm not sure. I haven't thought about it. OK. So let me talk about putting an ominimal structure in the context of hard structures. So I can tell you how, I haven't read the whole thing, but I can tell you my understanding of it. So for example, if you think about like a curve, like the easiest case is take a definable function from C to C and say, is it algebraic? Well, because it's definable, it actually has to go to infinity at the boundary. And so then Louisville's theorem tells you it's algebraic. The general case is more difficult than that. But in some sense, it's a similar kind of picture where you have some sort of control over the level sets. And that control is enough to rule out essential singularities, which is what you're fighting, basically. Yeah, but they do, in fact, I mean, they do reprove Chow's theorem in a different way. Because if you're actually projective, then you're actually analytic and you're definable in Rn. So somehow the theorem really is, I think it really, I mean, my understanding is it is an actually different proof of Chow's theorem. OK, so let me talk about what happens in the algebraic set, in the hard structure setting. So we have this map from omega to omega mod GZ. And this usually happens, this map sort of has infinite monodromy, and so this map can't possibly be definable with respect to any definable structure here, because the level sets are infinite and discrete, and that's just not OK. So what we do is we take F to be a fundamental domain for pi. And then we have an isomorphism.
You need that to be definable in fundamental domain?
We don't need anything at the moment. Well, sorry, I guess you do. You're right. So if you have fundamental domain, you have this map here. And this is an isomorphism, so I can take any structure which exists here and put it over here. That's sort of just very easy to do. And so yeah, as long as F is definable inside here, it has a definable structure. And so we can do that. So this part's sort of easy. You don't have to work at all to put a definable structure in omega mod GZ. The hard part then comes in when you want to show that these period maps end up being definable with respect to that structure. That's sort of where, and for that you have to do something very concrete. All right, so let me state the theorem now. So we choose F to essentially be a Siegel set. Which you can sort of think about in a few different ways. You can actually take a Siegel set and cut things out of it. Or if you take a Siegel set, this is finite to 1, and that's sort of good enough to put a definable structure here. You can do it in a few different ways. OK, well, so then our theorem is that if S is an algebraic variety, actually, I guess we don't really need that, but whatever. If S is an algebraic variety, then the period map is definable. Yes, you use KAN, exactly. So I can say more concretely.
S is any base here.
Sorry?
S, capital S is any base.
Any algebraic variety, that's right, supporting a variation of hard structures. Then with respect to this structure we put on here, this map is definable for any base S. In fact, calling S an algebraic variety is a bit of a misnomer. The theorem really is about variations on punctured disks and potted disks and stuff like that. And then varieties are covered by finitely many of those, and so you're fine. But for what I'm talking about, yeah, let's stick to algebraic varieties. OK, so let me say sort of concretely what our Siegel set here is. Again, more or less. So concretely, with respect to this ominimal structure. Sorry, I'm not sure who has the questions. I'm not sure who I'm looking at. But, oh, OK.
Where did that one come? There were 3 choices on that board. Behind you.
Behind me. This board?
That board.
This board here?
No, if you walk past it there.
This one here? Oh, sorry. So yeah, I should have said. Sorry. We use RNX. We always use RNX for everything. Yeah. These two are just too small to handle any holomorphic functions at all, somehow. In fact, this one doesn't. They prove Pirzun-Starchenko that this structure doesn't actually add any holomorphic structures. Real exponentiation is not enough for that.
You know, in the notion of hyperbolic, in Lang's work where he tries to formulate the finiteness conjectures, one of the notions you're forced to make also essential singularity in the definition of hyperbolicity. You know, if it's all related. In other words, if you just take polynomial maps, that doesn't give you the equivalence of Kobayashi, Green. There are all these equivalent notions of hyperbolic.
Mm-hmm.
And the most interesting one forces you to allow essential singularities.
Mm-hmm.
Maybe there's a relation.
It's possible. I haven't read about that. Yeah, I'm not sure.
Because you're only adding x, right?
No, we're adding exp and all subanalytic functions.
Yeah, yeah, of course.
Yeah.
I understand.
Oh, okay, yeah. But only exp is the only one that gives you interesting behavior at infinity is exp. That's right. That's the only one that gives you interesting behavior at infinity.
I mean, that's the answer to his question of why x. Yeah? I'm just trying to understand why only x.
Oh, I see.
I think that this essential singularity is captured. Anyway, I don't know.
I'm not sure. Yeah, yeah.
So subanalytic mainly means that if you have a unit rule and something analytic, you put it in.
Exactly. Well, something analytic which converges on a bigger ball. Yes. Then you put its graph inside. Exactly. It's just adding all of those things in. That's right. So yes, everything with respect to the structure Rn exp. I'm not sure why exp comes out. For us, it comes up essentially because of q coordinates for the upper half plane.
Direct function that is-
Yeah, it's very explicit. I don't know of a more philosophical reason for why this is the correct structure. Yeah.
Of course, you could put more.
Yes, you can certainly make it bigger, and it would be yes, but you'd have to be. And there's constructions. You can take like Pfaffian enclosures of things, and they'll still be ominimal, and you can do various things like that, and make the structure bigger. Yeah, but this is all we need. Almost exactly what we need for a theorem.
Eisenstein theory is definable.
Sorry?
Eisenstein theory is definable.
On the upper half plane? Yep. There. Other questions? All right, so let me say concretely what our Siegel sets really are. So concretely, if you take V1 to be M to be a basis of what we called L at the beginning, then concretely what you can do is you can insist that V1 through M to Vm form essentially a Minkowski basis for the Hodge metric at a given point. And the subset cut out by that, you can insist that that essentially gives you a Siegel set. So basically, concretely, it can be a basis. So F is the region where sort of two things happen. So what does it mean to be a Minkowski basis? So if you look at the product of the Hodge norms of the V sub i's, this is not much bigger than 1. It can't be smaller than 1, but it's not much bigger than 1. I haven't defined Hodge norms, but you can put a Hodge metric at a given point once you have a Hodge structure. And the second one is that if you look at the Hodge inner product between two different guys, it's not much bigger than the norm of either one of them. So this is what an analyst thinks of as a Siegel set, at least what I think of. There isn't any k decomposition method of doing it. If you do it for GON, you essentially get this sort of classical notion of a Minkowski reduced basis. And these guys naturally map to GON via the Hodge metric. So this is essentially what it comes down to. And so I don't want to give the impression that we're sort of saying, well, there were analytic ways of doing it, but now we have this much better ominimal ways, so let's throw those out the window. In the proof of this theorem, we heavily rely on previous analytic tools. So for example, that they didn't state it in this language, this theorem was essentially proven by independently by Kashiwara and Kantani, Kaplan, Schmidt. Who sort of gave asymptotics for in Hodge variations how things behave. So by which I mean that if you take a period map, then you can pick a basis to essentially satisfy this kind of thing. That was proven by their works. And this over here was proven by Schmidt, again, not in this language, in the one-dimensional case. And so actually, what our proof does,
Do you mean that you restrict to some near infinity of n?
yeah, so
Universal covariance and some fit to
right, so
properties?
let me write down concretely what I mean, which is if we have a map, say a period map, from some punctured polydisk, delta star to the r, into omega mod gz, we can cover this by the upper half plane to the r, and we can cover this by omega, and then we can lift, so call this phi tilde. And now in h to the r, what we do is we look at v to the r, where v is some vertical strip. And what I mean is if you do this construction, then on v to the r, these properties should be satisfied, is what this theorem basically amounts to. And we're sort of relying a lot of asymptotics. So yeah, there was on domains like this, these two papers sort of deal very explicitly with how individual vectors vary. And then Schmidt does some magic, some very interesting differential that I don't quite understand still, that amounts to proving this kind of result in the one-dimensional case. And so our proof essentially ends up sort of piggybacking on Schmidt's work using this result to sort of extend this from one-dimensional families to the general case, essentially because surfaces have lots of curves inside them, and we sort of use this to our benefit. So I don't want to go into the proof, let me say, at all. So instead, I want to give an example of the kind of thing this is useful for once you actually have it. So one sort of strong piece of evidence for the Hodge conjecture is the theorem of Catani-Delisle and Kaplan, which says the following thing. Suppose S is an algebraic variety, and you have a local system over it, and you have some variation of Hodge structures. So you have some Hodge filtration here. And now take V to be sort of some local section of L. So there's monodromy, so you can't take an actual global integral section, but you can take a local section over like an open disk or something. And then you can look at the locus where V is Hodge. So where V is inside the middle Hodge piece, the pure piece. Now, if the Hodge conjecture were correct, and this were an actual variation coming from a smooth projective family, the place where V is Hodge is the place where you have some cycle over your point. And that's an algebraic condition. And so it would follow that this locus is algebraic. And so the theorem is that this is, in fact, algebraic. So in fact, more formally, or actually stronger than that, Catani-Delisle and Kaplan. There's the following theorem. If you look at the subset of points which have integer vectors with just bounded Q norms and which are Hodge, this entire locus, which is some global thing, because now we're not taking monodromy into account, then this is algebraic. OK, so this is sort of a perfect example for what our theorem is good for. Because how would you prove this, for example, in weight 1, where you have a Shimura variety, AG? Well, you would say you have some map from S to this space. That map is algebraic. This locus here is algebraic. And so its preimage is algebraic. And you would be done. There would be sort of nothing to do. So in this case, we're going to do essentially the same thing. So this is an alternative proof now using these methods. But instead using definable chow in place of algebraicity. So look at this locus star. So in omega, you can show that star, the locus where this is true in omega, is given by a union of sort of semi-simple orbits of a single point, and then translates of those where H is the stabilizer of one of these vectors V inside G. So it's some purely group theoretic thing, regardless of what it is. Then by sort of standard Siegel set theory, due to Borel and Harish-Chandra, implies that this locus, mod GZ, is definable, basically showing the intersection of this with Siegel sets as some reasonable object. And so now, if you have this period map, let's call this locus W. We're basically looking at the locus phi inverse W on S, so the points on S where this kind of thing happens. And we know that this is complex analytic, closed, and definable. And therefore, by definable Chow, it's algebraic. So you can basically make the same argument to work. You can't apply definable Chow on omega mod GZ itself because it's not algebraic. But there's all these algebraic things mapping into them, which, as soon as you pull them back, as soon as you pull back definable analytic conditions, you get algebraic things on the base. So that's basically the idea behind this method. You can sort of prove other things with respect to Weil Jacobians and other finiteness theorems of that sort. And we're now trying to make this technology work for mixed Hodge structures, where you'd recover things like the theorem of normal functions and stuff like that. But I think I'll just stop here. OK, thank you very much.
This is for any ominimal structure?
Yes, that's for any ominimal structure. That's right. So the hard usually you have some set, and you could just say, look at the smallest structure containing this set, and if you can show that's ominimal, then you're good. But in practice, it's much easier to work with given ominimal structure, just prove something is definable in that structure.
Can you compare, just maybe briefly, what the original proof of this is?
Sure. Well, so the original proof sort of went in. It went into these kind of arguments for sure, and borrowed the same estimates. It was an inductive proof using the asymptotics. I mean, the hard thing to show is going into it a little bit. In general, you have like in 2 dimensions one long vector, or let's say 3 dimensions. You have one long vector, one medium vector, and one short vector. And you can say the long vector goes out of the window, and then you have the medium vector, but then you could add short vectors to it. And so you get this issue where you have possibly countably many holomorphic things instead of finitely many. There's this sort of nilpotence issue that comes up. And so the main thing the original paper does is sort of deal with that issue. But I don't understand the argument well enough, certainly at this moment, to say that much about it. Yes, please.
Instead of using definable flow, we have to use that something of finite volume and analytic is algebraic.
Right. Yeah, so I think you also go into this set a little bit in omega, but in some sort of, in a different way. Yeah.
There's a conjecture saying that phi s is algebraic in your theorem. So that gives, but is your definable structure, is that compatible with that one?
Yeah, so I think that's a proven conjecture, right? I think it's a theorem going back to. No, so recently, right, so I think it was a theorem a while ago due to, I forget the name, but there was some paper that did it early on that showed the image algebraic variety. Very recently, work of, who were the authors, Ben, do you remember? Griffiths.
Green, Griffiths, Robles, and Lazo.
Right, Green, Griffiths, Robles, and Lazo. They showed that it's algebraic. They gave a natural compactification of the image and they showed that the Hodge bundle was ample. So they do quite a bit more. And so their point is there's no Bailey-Brooke rectification for Hodge structures, but they can do it for every algebraic variety one at a time. It's a little bit of an orthogonal issue. I mean, we can show using this that it's algebraic, the image is algebraic, just because a quotient of an algebraic variety by definable relation is definable, and then you can show it algebraic using those kind of methods. We can't recover their thing. It's a little bit different because they sort of show that it's an algebraic objectification exists, which is not, oh, my time is up, or is that? Oh.
Joseph, I think this might be yours.
Sorry. So what they show is that they essentially give a nice parameterization of different ways you can go to infinity. But they don't really tell you information about the asymptotics of how you go to infinity. So for example, their theorem applied to like a single punctured disk tells you there's a well-defined mixed Hodge structure at the limit. That's all it says. But it doesn't tell you the speed at which you go to it. And it doesn't really give you information about anything like this, which is what you need for this theorem. And our theorem doesn't really recover their work. I mean, they're sort of orthogonal questions, even though they look very similar at first. Yeah.